Giving us that great overview of planetary science. Now, next up, I'd like to introduce Dr. Karen St. Germain, our Earth Science Division Director.
Thank you. Hello, everyone. Can you all hear me okay? A little thumbs up if you can hear me. Have to hold it a little closer? Is that better? Okay, awesome. It is great to be here. I love coming to AGU. And today I'm going to do something a little bit different from what I usually do. I am going to talk to you today about our oceans. And within about 15 minutes, I'm going to have you convinced that even if you don't think you care all that much about the oceans, you really do. So, why are they important? Our oceans. Do we have any engineers in the group? Any engineers? Okay. Our engineers, at a minimum, know that an engine is something that takes energy and converts it into motion. The oceans are the biggest engine of them all. Our global ocean is the biggest. It's a planet-sized engine, and it's pretty powerful. It's a couple of its features. It's very slow to warm. You have to add a lot of energy to the oceans to get the temperature to come up. You know this because you tried to boil a pot of water for pasta before, right? You have to add a lot of energy to get the temperature to come up. But once the temperature is up, water is an incredible storage tank for heat. Our oceans store a tremendous amount of heat. And that's really what makes life on Earth possible. Do we have heliophysicists in the audience? Any heliophysicists? One. Okay. This is for you. Our Earth intercepts 1/billionth approximately of the energy that the sun puts out. About 1/billionth. About half of that is in the visible part of the spectrum, and about another half of that energy that we intercept is in the infrared part of the spectrum. In our oceans, the infrared energy barely penetrates at all. It just makes it gets absorbed in the surface, and then it gets re-radiated back out. It's actually the visible energy. So, I should have said, we intercept 1/billionth of the sun's energy. About a third of that is immediately reflected back out into space. So we've got 2/3 of 1/billionth that gets absorbed, and half of that is infrared, and it immediately gets re-radiated. So that it's that other half, that visible part of the spectrum, the energy in that visible part of the spectrum that is warming our oceans. And the oceans store that energy, and that is what makes life on Earth possible, as we understand it. The story of our oceans is the story of life. All right, so just a couple of years ago, we launched the SWOT satellite in December of 2022. The SWOT satellite is an altimeter that images in a way that we have never been able to before. It's an interferometric altimeter. And what you're seeing here is variations of the surface, of the height of the surface of the ocean. So don't want to fall off the stage here. So red is a little higher than the average. Blue is a little lower than the average. And the scale here is 25 centimeters in either direction of average. All those features, so I bet many of you probably thought the ocean's pretty flat. Well, it turns out we can see variations in height on the order of 7 inches or so from space, and all of those are real. What happens when we have eddies in the ocean, we've got upwelling and downwelling circulations, and the upwelling circulations cause a little divot in the surface of the ocean. Likewise, the downwelling causes a little bump in the surface of the ocean. So what you're seeing here is circulation patterns in the ocean. You're seeing currents, that's the Gulf Stream, and you're also seeing all of these little eddies. So this is an unprecedented view of our oceans. We've never been able to see the ocean motion. I like that, ocean motion, at that level before, and it is challenging our models. we've had ocean circulation models. The one we're looking at here is the ECHO model, and we've been pretty proud of the ECHO model for a long time. And what you're looking at here is surface current speed around Antarctica as an output of that model. Well, what you're looking at over here is the gradient in sea surface height in SWOT data. So I told you that when water moves, it either elevates or depresses the surface of the ocean. Well, what we're seeing here is a lot more energy than we thought, moving water up and down in the column. This is the first time we've had data that can challenge our models, which is awesome. There may be processes that we don't have exactly right, and we've never had the data that can drive the models before. So once we figure out how to ingest all of this data into that model, we're going to have an unbelievably accurate view of how water is moving in the oceans. All right. So that was SWOT. Now I'm going to talk about PACE. PACE is the second major ocean mission we've launched just in the last couple of years. In fact, this one just launched earlier this year. So this measure, PACE does something different. PACE is a hyperspectral ocean color instrument. So we've been flying ocean color instruments for quite some time. I mean, going back 20 years with CWIFs and MODIS and so forth. But PACE gives us high definition that we've never had before. The big difference is that with the full spectral information, it's like seeing the fingerprint of the organisms that are living on the surface of the ocean. All right, so why is this important and what are we looking at? Well, now we're looking at aerosols. A minute ago, we were looking at phytoplankton. And, phytoplankton are fascinating. They do the same thing that plants do on land, which is they take the sun's energy, CO2 or carbon dioxide in the atmosphere, nutrients, and water. They take those four things and they turn those four things into something that the rest of the food chain finds very useful. It's the same thing that plants do on land, right? All life on land starts with plants. So phytoplankton serve that same role, and it's an incredibly important role. It takes CO2 out of the atmosphere. It serves as the basis for the entire marine food chain, and so forth. Well, what we can do now with PACE, we've always been able to see chlorophyll, but for the first time now we can see pigments in those little phytoplankton. They're little wee beasties. And because we can see the pigments in them, we can now start to differentiate between different species. I say that and it's not exactly right. You never see a big colony of only one species. They live in communities. So what I'm really talking about is seeing different types of communities, some of which are really delicious fish food, some of which are toxic. And so we can now see from space in the early stages what type of phytoplankton is growing. PACE also has two polarimeters that look at aerosols in the atmosphere, and that's really important because that's one of the mechanisms by which nutrients get delivered to those little phytoplankton. All right. So I talked to you about SWOT. I talked to you about PACE. Now I'm going to talk to you about the kinds of things you can start to see when you combine the two. So you're looking in the background at PACE data, and the overlay is SWOT data. So we're overlaying the biological and the physical action in the oceans. Why is that important? Well, I told you the four things that phytoplankton need to live. They need light. That means they have to be up close to the top of the water column because the light doesn't penetrate that far. So they need light and they need nutrients. Carbon dioxide, that's easy. If you're up near the surface, you're near the carbon dioxide. You're in the water, so you got the water. So the real two variables are sunlight and nutrients. In the upper layer of the atmosphere, and when I say upper layer, I'm talking about 60 to 200 meters. There's lots of sunlight, but the nutrients get used up pretty quickly. The phytoplankton gobble them up. Down below, you have very little sunlight, but you have lots of nutrients. So basically, the energy that creates life and the raw material, they stay separated in two different layers. They only mix when water is moving up and down. And that's what I told you we could see for the first time with SWOT. Right? So you have to have that mixing for life to grow. And so one of the things that you're seeing here is where we have a little dent in the surface, we're seeing upwelling from the depths of the ocean, carrying nutrients, and then you start to see phytoplankton growing in these places that are far away from land, which is the normal delivery mechanism for nutrients into the ocean. All right. How am I doing on time? All right. Okay, so why is this important? Well, it's important for a whole lot of reasons. The ocean, one of the things it does is it carries heat all around the planet. So most of that energy from the sun, most of that's coming in pretty close to the equator in the low latitudes. But it doesn't stay put. The ocean currents move it all around the planet. One of the places it moves it is to the Arctic. And one of the things that's happening there is we're seeing a pretty dramatic reduction in sea ice in the Arctic. That's a problem because ice is white. It's part of the mechanism that reflects energy back into space in the northern latitude summer. So with less ice, we have less energy getting reflected, even more energy getting trapped in the Earth system. So really, and as that ice gets thinner, it's more easily broken up. We don't think about it, we don't see it on the news, but there are storms that cut across the Arctic that are the size of hurricanes. Well, if that ice is thick, it kind of stays put. But if that ice is thin, the storm will break it up and it'll melt faster. So we're seeing some feedback mechanisms here that have global implications. All right, let's talk about weather for a minute. Anybody here care about the weather? Anybody? Yeah, bunch of people. We care about the weather. All right. When I worked at NOAA, one of my colleagues there used to say, if you like your long-term weather forecast, thank an oceanographer. Because all of the weather starts with the oceans. Temperature is a marker for energy, how much energy is in that system. So the way this works is the oceans warm up because the sun is warming them. The atmosphere is terrible at holding heat, so it's the oceans actually that warm the atmosphere. So think of the oceans as sort of a hot plate, warming the atmosphere above. So the oceans are really good at storing energy. They're really slow at moving it. It takes, it's measured in hundreds of years to move energy all the way around the planet. The oceans move slowly. The atmosphere is just the opposite. It's terrible at holding energy, but it's really good at moving it. So think of the oceans as the warehouse, think of the atmosphere as the transportation system, and that's how energy moves around the planet. So what you're looking at here in the upper left is sea surface temperature in the Gulf of Mexico during Hurricane Helene, and those temperatures, I have to check my notes because I kind of can't believe this number. The temperature in the Gulf of Mexico when Hurricane Helene was strengthening was 27.8 C or about 82 Fahrenheit. I don't even want to take a bath in water that warm. It was really warm, and that's what provided the energy for Helene as Helene strengthened through the Gulf. In fact, it was a rapid intensification event. I'm showing you Helene here, but everybody remembers Hurricane Milton. Milton was also a rapid intensification event, very, very similar. And In the case of Milton, it went from a category 1 to a category 5 in 24 hours. Now, there's a little bit of a misnomer. When we talk about categories, that's pegged to wind speed. That's actually not what kills people most of the time. Most of the time, it's the water that kills people. And in Hurricane Milton, which is the one that went across Florida, that was carrying about as much water as we have ever seen a hurricane carry. By the way, when I talk about the energy in the oceans and the energy in the Earth system, these are unfathomable numbers for us mere mortals. But to give you a sense, that energy, that process of the ocean warming the atmosphere rising, carrying water up with it, in one day, that energy moves 1 trillion tons of water from the ocean into the atmosphere. It's an unfathomable amount of energy. And that's what gets unleashed when we look at these hurricanes. Okay, so I've talked to you about some of the cool things that we can now see for the first time, including the physics of the ocean, including the biology of the ocean. What's this thing? Well, this is our new NASA Earth Science Strategy. We call it the Earth Science to Action Strategy. And here's what it really means. It's one thing to observe and learn and understand. But we think the power of science doesn't get unleashed until it's in the hands of people who can use it to make better decisions where they are, when they need to make those decisions, in whatever jurisdiction we're talking about, from households to communities to businesses to states and nations. So the strategy here is to accelerate our pace of discovery and the pace of getting that information out into the hands of people who can use it. And then bringing the learning from that process back in to help inform future missions and our science investigations. All right, here's an example. And I think, yeah, there we go. So here's an example. This is a multi-agency sea level rise tool. So, we have these models. We understand for different emission scenarios how, what the probable sea level rise is. So we developed a tool that people can interrogate. They can go in and look at their own, coastal community, their own hometown. Here we're looking at Solomon's Island. Anybody been there? It's right down the road. It's a pretty awesome place. So Solomon's is a coastal community in Maryland. And Solomon's Island has seen about 11 inches of sea level rise since I had to check my notes again. Over the last 55 years, 11 inches over 55 years. We project that over the next 25 years, they'll see another 11 inches. So it's almost a doubling, the same amount of rise again in just about half the time. All right, so it's one thing to tell people what is the level what is sea level going to do over that period of time, but what people really need to know is how often is it going to flood, right? That's actionable information. That's understanding how coastal homes and businesses are going to be affected. So we translate sea level rise into high tide flooding events. So we're not talking about storm surge here. We're talking about flooding that happens just on a regular sunny day with high tide. So in the 1980s, Solomon's Island saw typically 3 sunny day flooding events per year. 3. That was, the 80s weren't that long ago. At least I think so. In the 2010s, so last decade, that number went up to 48 flooding events per year. And we project in an intermediate scenario, so intermediate emissions scenario, not high emissions, not the worst case, that by about 2050, in the 2050s, they will be seeing 130 flooding events per year. So these kinds of tools can help communities really understand what they're facing as they're making infrastructure investments and so forth. 3 minutes. All right. So what's coming next? The next mission we're launching that gets added to this cadre is the NISAR mission. NISAR will see changes in anything that is structural in nature, from stands of forest to buildings to glaciers. Anything that changes its position, NISAR will see at the centimeter scale. This is really important for our oceans. We'll be able to see, for example, whether we still have stands of mangroves. We'll be able to see glaciers calving, which adds water to the oceans and so forth. So there's a third piece of the puzzle, the oceans puzzle, that is going to come online. We're looking to launch in early 2025, and we can't wait. So I hope I've convinced you that the Earth is a system. What we're looking at here is our NASA fleet of about 25 missions that are looking down at the Earth, measuring different aspects to see how the whole thing fits together. And I hope that whether you are an ocean scientist or, where is my friend Dwayne, a farmer from Kansas, you care about the oceans. You care about the oceans because they drive weather, they drive much of how life plays out on our home planet. I think that's it. That's it. Thanks very much.